I will try to present the presentation by Tassos in my best way. Excuse me if it will take some time because it was not prepared by myself. These are the people that are contributing, and many, many others which could not be presented here, individuals, governmental and public authorities, and both in Greece and in Cyprus. The outline is, Tassos took the occasion of this to make a short presentation of what we can make. So it is a very, very short presentation of the laboratory. And then he has presented the whole thing on what kind of data we need, mainly for the microzonation studies, but not only, and how we can validate this in order to do what? Not the full microzonation study, because it needs hazard and everything, but the data that we need in order to model side effects. And he has presented a number of microzonation studies in Greece and in Cyprus. We have done also in Turkey. What is very important is that this lecture, as I said, is not going from A to Z regarding the microzonation studies. We concentrate ourselves here only on the geotechnical part of the microzonation studies and the side effects. A very important issue that I have been already started talking about is the scale effect. And when we are speaking about the microzonation studies, we speak on urban scale, means the district or the city level, not the single structure. Of course, we can use it, but this is the very important point which makes probably the microzonation studies not very appreciated by, let's say, the community of our geotechnical engineers, because they believe that with the existence of a microzonation study, there will be no work for them. I am a geotechnical engineer, so no. The problem is that it is misunderstood. The microzonation study is not going to replace the detailed geotechnical, because it is first in other scale, and then it is not mainly focused on the design of the, let's say, of the single structure. It goes in other scale, and it has other purposes for land use, for, let's say, risk in urban scale, etc. So this misunderstanding is not only here, is almost everywhere in the world, and this is a problem. Anyway, there are several research projects that have been produced, everything that you will see later on, and a lot of microzonation studies in here in Greece and in Cyprus, also in Turkey. Okay, something about our lab. It is well known. It is a laboratory that has a lot of capabilities and possibilities, from laboratory research, from in situ surveys, and of the analysis of all this. Probably we should make in another occasion a good presentation of the Eurosite test and Europroteas testing facility or experimental facility, which is rather unique in Europe, and now I would say in the whole world. But we will not spend much time on that. Okay, there are a lot of instruments that we bought all these 30 years. We can conduct any kind of studies, and as you will see, including a small shaking table, which now will be improved. I don't know if Dimitris is here. He will have the possibility in a year from now to have in his capacities a much bigger shaking table, and I hope that he will be able to do a lot of things with that. And the field, mainly with, I don't know if Raptakis and Manako are here, have been really, we do everything that is related with the geophysical and seismic surveys all over the world. And something which is presented for the first time, George, we will have probably the more dense strong motion stations in Europe, and you can see here the TESNet with almost 70 instruments in free field or in buildings. And it will be with the help of the region of Central Macedonia and of the Technical Chamber of Greece. And we believe that in 1 year from now, all this array will be 724. It's working. It will be even with the small earthquakes, even for the weak part, it will be extremely important from many points of view. But it is the first time that I'm presenting this one. It's not ready yet, so maybe next year. Now, I'm concentrating to the microzonation studies. So everything that you will see are more or less based on the work done in these microzonation studies. And there are some manuals that you know probably very well. These are the 4 major documents that we have, but we have been based a lot on our own experience. And in a certain degree, some of them have been, let's say, somehow influenced or improved by our own work. We will not work on the seismic hazard. We will be concentrate ourselves on on this part. And the aim will be to produce the necessary data and models in order to conduct at least 1D side effect analysis. So I'm going fast here, it's not necessary. Why? We need this because the wave propagation, we know that is working like a filter or a kind of amplifier of the ground motion. We need, of course, the dynamic, physical, and dynamic properties. It is a misunderstanding in the writing this. But we need the strength parameters as well, for example, for the liquefaction. A big problem that we have is the description of local and spatially distributed soil conditions, because for the microzonation it is important. We come with this in the scale effects, and we should not neglect the nonlinear behavior. All these are target to study these problems, mainly for the land use planning, for risk studies, interpretation of damages, and modeling and understanding the side effects. So the whole story here is to come up here. The way that we can design appropriate, let's say, models, 1D, 2D, and 3D, and perform side effects analysis. But to come here, we have to validate these estimated values of the geotechnical parameters. It is rather difficult to do this, but anyway, I will try to, at least through the presentation of Tassos, to show the way that it could be done. These are the microzonation studies that have been, let's say, performed by our lab in Greece and in Cyprus, and once in Turkey, in Duce, after the 99 earthquake. This is the case of Thessaloniki. I'm, let's say, I'm going very fast, and you have already seen some results on that by EVI, for example. This is in Cyprus. We have done already three microzonation studies, and now we are working on the fourth one in Chrysokous. So we cover almost the whole, let's say, free, that's Cyprus, the Republic of Cyprus. The first thing, and this is a big problem and we have not solved it at European scale, is the collection and evaluation and organization of the data. Why? There is this geospatial data. We use it, and we come up with this kind of things. But it is not really very much used from many points of view. And this is, in a certain degree, the fault of the practitioners. Yes, I'm right? But there are other problems as well, because our personal data, and maybe an individual wouldn't like to share the data with another one. So it is not an easy problem. But anyway, we need it more and more. In particular, when we are going to use artificial intelligence and machine learning and whatever in order to get a better global picture. We start with the geology. This is simple because in general, geology is free and we know it. And then we need a lot of geotechnical data. There are few cities where we have a lot of data, like Thessaloniki. In other cases, we do not have. And I would say in most cases, we don't have. And if we have, they are not free. So so for this reason, we go to proxies, as you have seen in the presentation of Evi before. Fortunately, in Thessaloniki, we have a lot of them because through several research projects we have done a lot of cross-hole, a lot of downhole, a lot of microtremors, a lot of array measurements of microtremors, a lot of any kind. But it is because it is our city and we know how to do it and find the right people. And okay. And then we have to make them all in a way that we can arrange the different statistics that we have to do in order to come up with this kind of a geotechnical map. Now, if I was a practitioner and I would going to see this kind of map, I will not be very satisfied because it is very detailed. It is the work by Tassos because it gives in every point A, B, E, F and a very detailed description of the depth, 2 to 3, for example, here is in this is 2 to 13 meters, the soil type A, the B1, the B2 is our own classification of our lab is 2.20, and then we have the EF. So for the application of the seismic code, it is a kind of a thing because they are all there. With a lot of details like this. And a lot of statistics. I give you some typical examples. And we come up with this kind of nice maps. If I have a couple of minutes more, dear President, I would say that this map, this small map here, changed the history of Thessaloniki and has an important, let's say, a political effect in the whole, let's say, Greece. Why? For the Greeks, it is very well known. The struggle and the battle about the Venizelos, about the metro line, and the Venizelos station. We have produced this before the starting of the metro line. And it was Bouygues who got the project with the idea based on the call that the line will go not more than 6 or 7 meters below the actual surface. And the director of the Bouygues, he came in my office and we start discussing, and I present him this one, where we have the debris which goes down to 17 meters and more. But his offer was for 6 meters. In a month, Bouygues and moved away. And we spent another 15 years in order to start working on this. And a lot of political battles, why you have done this, etc. So, let's say sometimes the geotechnical issue has a great political effect of any point. So these are the kind of maps that we are producing for Thessaloniki. In other parts of the world, like in Cyprus, you see the geological map again. We see a different type of studies that we have done in cooperation with the local authorities, with a lot of cross-hole, downhole, and other kind of in situ surveys. And we come up with this kind of geological maps in Paphos. If you want to find the most complex from geological point of view place in Europe, go in Cyprus. It is unbelievable. Nothing similar with Romania and with our case in Greece. It is everything like this, unbelievable. It is extremely complicated, and this is the reason that all the geologists in Europe, and not only, they are very fond of Cyprus, and for other reasons, of course, for Aphrodite and etc. But it is really the best example that you can see of complex geological. But for us, it is. We have to give a solution, let's say a number, and it is a cumbersome. This is the place of the free Ammophostos. Again, you see how complex it is. With the existing boreholes, not only from the geotechnical point of view, but for other, let's say, for other circumstances. These are the extra data that we have and we have done for the purposes of the Microzonation study of Ammophostos. And we come up with this final geotechnical map. Even this geotechnical map is very complicated, even this one, which should be as simple as possible. Of course, in any point, we have all the details. And in some cases, we have found some soils that should not be expected there with very high plasticity clays. So it is the most difficult case that we had seen so far. So the lessons learned, more or less, are that we need the geospatial data at large scale, and they are not really available as we wish to. The geotechnical engineers should make a preliminary elaboration of the data that they hand in hand, but they have to be experienced, and they should have a good knowledge of the site geology. And we have to combine lab testing with good in situ testing, in particular for the strength, and not only SPT, CPT, and other surveys. Now we go to the dynamic part. Again, in the lab, we can do almost everything. For the resonance column, we have done mainly Anastasiadis, more than 1,500 tests so far. For the cyclic triaxial, more than 1,000. The Bender elements, which is much more easy and fast, but not very, very much accurate because it is in a very low amplitudes. And now we start also introducing in the whole game the shaking table, and we can see some results. It's by Tassos. Is Tassos here? Is Kapouniaris? No. He's working for his thesis. He has to present it in few months. You see the range of shear strains that we have. The problem is that we need all of them, actually, not only the resonant, because it is limited as the range of application. We need all of them, but this is much more expensive. And you see the type of data that we have. This is, for example, for the liquefaction. And if I'm going to use these typical curves that we are using everywhere now in our studies, and we have only the Bender element, we know that we are only in this part. If we have only the resonant, we are in this part. If we have the cyclic triaxial, we are here. And if we want to go to the very large shear strains, we have the capacity, to use shaking tables and go even further. These are typical results that came for the different cases that we have in Ammochostos. A first thing that we can see here is that still we have a lot of uncertainties. There is a scatter, of course. So it is some way we have to decide that we will use an average curve but the good thing is that with the existing generic curves, even starting from seed, they are not so bad. We are more or less at the same range. This is the good thing, of course. Not for the damping. The problems we have is not for the G-gamma curves, it is for the damping, where we, in general, we cannot, I'm not saying that the generic curves are better. I'm saying that the estimation in the lab of the damping is more difficult. So we have to be more careful when we are proposing the damping. And of course, we have to propose also some correlations between VS and NSPT, because we have thousands of SPT, but we do not have a lot of VS. And there are also hundreds of correlation curves. We try to compare this with our own data, and in general, it's going rather good, except if we have artificial or very complicated soils. For example, in Thessaloniki, it is our big problem, because the first 10, 15 meters, let's say 2 to 10 meters, it is the old city of 2,000 years, so it is not a soil, it is everything that we can see here. But the problem is that the majority of our buildings are not going at -10, it is at -3. So probably they are founded on this soil, which is not soil. Anyway, we have not started working on that because it is another big problem. And why I'm presenting all this? In order to come up to the design of soil models. And we all using now at least the 1D, and in some cases some instrumental, the standard spectral ratio, H to V spectral ratio, GIS, and what you will see here is the combination of this with that in order to improve more or less the 1D soil model, which is used, the shake approach, for example, which is widely used everywhere. The case of Thessaloniki, we have a lot of data here from cross-hole, as you can see, from downhole, spectral wave, etc., a lot of things, even for the damping. This is the kind of logs that we have in many parts in Thessaloniki. This is the type of data that we have from the lab testing. These are the proposed, many years ago, G-gamma day curves, the typical curves that we are using for all types of soils that we have in Thessaloniki. So in Thessaloniki, we know exactly for each type of soil that we have, and there are about 10 these curves. Sorry, this seems that it is not in the sea. It should be, if I remember well, it is the white tower, so this must be around here. It is the log of in the white tower place. We produce this with a lot of data and a lot of cross sections, as we can see here. We make a kind of effort based on 2D soil models to come up finally with this kind of things. This is where is mostly between the university and the center of the city, Intramuros. And you can see that we have, it is not so steep. This is about 6 or 7%. So here is about 40 meters. Here is about 150 meters. And then to do the microzonation study, we have to make 1D at least analysis in a certain grid. The more data that we have, we can do it in a more accurate and safe way. If we have few data, then the scatter and the uncertainties will be much higher. In the case of Thessaloniki, we can do it in not so coarse, I would say, in a very small spacing. The case is not the same because we had not a big budget in other places, in Cyprus, for example. This is in Paphos. And in Paphos, we have done a lot of array measurements of microtremors. I do believe a lot on this because it is very cheap. And with the techniques that we have and the know-how, we can go, I would say, quite deep. If we have an aperture of, let's say, about 100 meters diameter, we can go down to 200 meters with a rather accurate estimation of the VS with depth, not an average VS, but as you can see here, a profile, and it is very cheap. Of course, we do need to have the geology. If we do not have the geology, maybe we go a little bit blind. We have done the same in Amochostos. I'm going fast here because the time is going fast. I'm skipping this because I would like to spend a little bit more on the validation. What we are doing all the times is to validate the 1D fundamental period based on our estimates with measurements. And the measurements are basically the H to V spectral ratio of some records that we have, either weak motion or some microtremors. If we have some records, even better. And for example, in Thessaloniki, we have this map of the fundamental P period. If, for example, here we have a 1D estimation of the shake, for example, and it gives a completely different, I'm saying fundamental period, it proves that this, let's say, is wrong. So we are using extensively in our studies the comparison, if we go in large scale, of course, not in isolated, for other purposes. We are using this kind of comparisons between the records to estimate the fundamental period and the data that we have from our field and laboratory studies, which are estimating the 1D profile. Of course, maybe Paco has some objections on that, but we must be from the engineering point of view, and we must be practical. We know that there are a lot of uncertainties behind this, but it is the least that we can do in order to compare and to be a little bit more from the safe side, let's say. So we are doing always this, and we expect that we do not have this kind of things, which is, again, the Thessaloniki with a very detailed stratification. And we know very well, and our good friend from Mexico, who is Chavez Garcia, is here. Thank you. It's Professor Chavez Garcia from the University of Mexico. With his help, we worked a lot on this kind of things, the 2D effects, or the 3D effects in some cases, which complicates the whole thing. And sometimes, if we will not consider this kind of things, maybe let's say, the standard spectral ratio or the H to V spectral ratio in order to compare with the 1D that we have estimated from borehole and from the data that we have from the lab is not so accurate. So we have somehow to, let's say, melt on this. And you will see in the presentation some comparisons that the people of our lab, and mainly Professor Aptakis has, and with Paco as well, have worked for many, many years now. I'm going very fast just to show you, because I'm not Anastasiadis, so I'm going to go in all this in a little faster way. The whole thing that we have to show you is that if we make the experimental site analysis based on the records, we can see that if we take only the S part, or if we take also the lateral propagation of surface waves, we may have different amplifications. And as you remember, our main comparison is between the fundamental period and the 1D analytical one. If we have this problem here, which is the real fundamental period in order to compare, is this one, is that one, or if we take all together? So it is not an easy game. You have to have some experience, of course, to understand the type of ways that we have and to make the best use of it. And this is not always easy. We would like to be like this, but the experimental, as far as I try to present it here, is not so straightforward. The 1D is straightforward. We have the 1D profile, you make the shake analysis, you find out the fundamental period. But if you go to the empirical, we have why? Because if we are sure about this 1D profile, we can use it then to make all the analysis that we need. And if we have this kind of things, which we have, this is purely, I think, numerical by Ratakis and al. And my Macra is not here anymore. You can see very clearly here the lateral propagation of the surface waves. And here you can see how well we have reproduced the empirical data if we are using the 2D. But the 2D is very complicated to do it in practice, so we must just have in mind that if there is a very complicated soil conditions and stratigraphy with the presence of 2D effects, we must be very cautious about the use of the experimental data regarding the weak motion standard spectral ratio or the H2B. The results are starting from the estimation of the bedrock motion. Okay, there are a lot of works on that. There is what kind of results we can have. This is in Thessaloniki. This is the distribution of the mean. Everything is done with 1D here. Distribution of the mean peak acceleration, the PGA, for different return periods. Just to know, here is the place of the airport. We are here, and this is the port here. So you can see the large difference. A big problem here is what kind of hazard we are using and where is the main faults. If you can see these values with the red, is because in this analysis, the seismologist, working with the seismologists mainly, they estimated, these are very old results, they estimated that a fault which is crossing here is the most dangerous for Thessaloniki, not the fault of the 78 earthquake. Now we have to repeat. Anthemundas.
Why on the piers you don't have any color?
Where?
The piers of the harbor, the wharf.
It is, no, we have here, this is the new pier here.
Yeah.
Is the sixth.
You don't have.
We don't have. Okay, we can, it is more or less the same, but anyway. The problem here is that the hazard is based on a mapping of the fault, which is not exactly what we could use now. It's something that let's say, I'm just giving this as an example. And the same is for the PGV, and the same is for something that is very useful for tunneling, for example, or other underground structures, to know the strains that we have at -3 or the stresses that we have at -3. And we can have this for the spectral values and different periods as well. This is the kind of data that we need. And then we have to produce in each zone the design spectra. The same happened in Amochostos, in Paphos. And again, the problem is what kind of geotechnical mapping you will use for all these kind of things. This is based on the Greek code, ABC. This is the EC8, based again ABC. This is the microzonation study. And this is, let's say, the use of the classification that we have proposed in purpose of the annex, of the national annex that we are going to use for the site amplification in Greece. It has been also something similar is maybe it will be proposed also in Bucharest, because we are working a little bit with Radu on this issue. Okay, I think that I can pass this. In order to stay a little bit more on the geotechnical exploration, we believe that the new technologies, which as let's say the drones or the machine learning or the remote sensing, and the satellite data, LIDAR, INSAR, and all these kind of things, may improve the classification and the zonation and everything, because they produce a lot of things. But let's say I use the we, but let's keep it as I believe that we have to invest a lot on the records. We have to improve as much as possible the records that we have, any kind. Fortunately, the accelerometers now with the MEMS are not so expensive. Instead of thinking of, let's say, 10,000 euros, you may have good data, depending on what you want to use it, with less than 1,000, which is very good. The problem is that if you have 10 instruments, you may use it and work with them by yourself. If you have 1,000 instruments, you need an army. And it's not so easy. We have seen this problem in Japan, where they do not have time to work with the KickNet data. They don't have the work to do it in depth. Of course, some crazy scientists, they are getting here and there, and they are open, but it's not really the way that they should do. The climate change, of course, a lot, the whole issue. And I do believe that this kind of efforts that I have shown you, our expectations for the next years to come about improving the data and the records, will give a step forward to what we want for the microzonations, for the site estimations, for the site effects, and for the way that we can use without being in conflict with the geotechnical engineering community, as I said from the beginning. I think that's all. And excuse me, because I couldn't follow exactly the presentation of Tassos. I just took it yesterday night, and I tried to make it as good as possible. Thank you very much.